Hello everyone, in this video we're going to discuss the concept of coherent demodulation as well as the superheterodyne, which is a form of coherent demodulation, as well as solving two example problems on the superheterodyne. So what does it mean by coherent demodulation? It means that we have a signal that has been transmitted and it is received, and at the receiver I'd like to demodulate the signal coherently, which means that I already know what the value of the carrier frequency is, and as well as I know what the phase of that carrier frequency is. So it's important to know the phase, as we're going to see in a moment. Okay, so if you know already what the value of the frequency and the phase, what you could do is that generate a local oscillator, the local oscillator generate that frequency and multiply it by the signal. Multiply the signal by that frequency. So the signal that has been received is x of t cosine omega ct, and I'm going to multiply it by cosine omega ct. If you do the math, you're going to get and pass this by the low pass filter, then you're going to get the signal x of t back. Okay, and that's the main goal, is that I'd like to get x of t back, right? Of course, up to a certain factor. So why is that? Why does multiplication by the cosine results in obtaining the signal back? Because the cosine, when you multiply it by another cosine, omega ct, okay, so this multiplication is actually results in that, okay? So y of t is equal to x multiplied by cosine, and I'm going to multiply the cosine by I'm going to multiply the y of t by a cosine, another cosine, which means that cosine squared will result in x multiplied by half and 1 minus cosine double the angle, right? Where does this 1 minus cosine double the angle come from? Multiplied by half. It comes from the properties of cosine squared. Cosine squared x is equal to half 1 minus cosine 2x. Okay? So if I pass this by a low pass filter, first of all, what does that mean? What does this parenthesis mean? It means that I have a value, a replica of the x of t centered at the zero. It's not shifted. Okay? Not shifted in the frequency domain. And another replica that is shifted in the frequency domain by twice the carrier frequency. Okay? And that's why when I plot this, that's why when I pass it by a low pass filter, I get the x of t back, subject to a scaling parameter. And that's why sometimes we put here a gain of value 2, so that it gets rid of this half. Okay, and in the plotting, in order you could explain it the same steps in the plot using plotting as well. In the graph in the frequency domain, this is the value of y of t, which is x of t centered at the negative omega c and the omega c at the omega domain. Okay, and when I multiply by cosine, I get a replica at the 0 and two replicas at twice this carrier frequency. Okay, so if I multiply this if I pass this by a low pass filter, then I'm going to obtain the x of t subject to a factor. And sometimes we put here a gain of 2, so we increase the gain of the low pass filter so that we can get rid of the half. Okay, and actually that's pretty much the same with if the carrier frequency was a sine and not a cosine. You could do the same steps, but remember, it has to be either a sine or a cosine. Okay, it has to be the shift of the carrier phase has to be 0. Remember that the cosine that I'm multiplying by here is the same as this cosine. If there is a change in the phase, then you're not going to get the same thing. So if you're multiplying by cosine ct plus theta c, although this was x of t cosine omega ct, then there is a phase shift between the two. And this phase shift is actually not going to result in a 1. It's going to result in a value less than 1. If the theta c was 90 degrees, you're going to be very unlucky. You're going to get a 0, which means that you're not going to be able to decode anything of this signal. Okay, and that's why it is called coherent demodulation. The carrier frequency and the local oscillator have the same phase. Okay, remember that there is one limitation in addition to that. In addition to having needing the knowledge of theta, you have another limitation, which is that this local oscillator is expensive when it is tunable. Okay, and that's why we have the problem. We have the concept of superheterodyne. So what does it mean to have a tunable local oscillator? Well, if you have a signal that is centered not at omega c1 but has another center at omega c2 and omega c3, well, is there an application that has this property? Well, yes. If you're listening to a channel at omega c1, you could want to change your mind and listen to another channel at omega c2, or perhaps change your mind and listen to another channel at omega c3. In that case, all what you need to do, all what you are hoping to be doing, is just change the tunable local oscillator and not throw away the entire radio and purchasing another radio to listen to a totally different channel. Okay, so that's what you need to do. You need to make sure that the radio has a tunable local oscillator. It turns out that if the tunable local oscillator is tuning at high frequencies, then it's going to be expensive. What do I mean by that? Let's assume that, for instance, this is at 800 kilohertz and this is at 900 kilohertz. So the maximum frequency is 900 kilohertz, and the minimum frequency of the channels that you're shooting for, you're intending to listen to, are between 800 and 900. Okay, which means that the local oscillator needs to have a range between 800 and 900. It turns out that if you because this is 100 kilohertz, okay, it is a large value, and you could even get a cheaper local oscillator if it was between 200 and 300. Okay, so even though the range is still 100 kilohertz, when the value of the center frequency is small, then the local oscillator is going to be cheaper. Okay, so what the superheterodyne receiver does is that it takes the entire signal and shifts it at an omega intermediate frequency. Okay, so it does it on two steps. It shifts it to the center frequency omega I, it's not zero anymore, and then after that it shifts everything to the zero by a second stage. Okay, so the local oscillator here, its value is going to be omega c minus omega I. Okay, so let's assume, for instance, that the omega I is at 600. So any value of the channel is going to be shifted at the omega I. Okay, whether it's at 800, 900, or 850, it doesn't really matter. The very first stage of the superheterodyne shifts at omega I. And then after that, a fixed circuit, when it is not tunable, where its value is equal to 600 kilohertz, is going to be shifting back from the omega I to the zero. Let's take this using plotting. So if I have omega I at 850, okay, sorry, this is 600, okay, and I need to listen to omega c1, then in that case I'm going to put the local oscillator at 850 minus 600, which is equal to 250. Of course, it's going to be shifted at a totally different value, but that's irrelevant for our case. Okay, so it's going to be shifted twice. Shifted here at the 600 and shifted here as well. So the local oscillator's value, when I want to listen to that channel, is going to be 250 kilohertz. If I want to listen to the green channel, omega c3, then I'm going to be shifting it by a value is equal to 300. I'm going to set the local oscillator to 300. Then in that case, it's going to shift that signal to the omega I, and it is going to shift that signal back to another value, which is to omega C3 minus omega I. Okay, and if I want to listen to the gray channel, then I could set it up to 200. Okay, so right now my oscillator is shifting between the values of between 200 and 300 kilohertz. So that's the cost of my local oscillator is going to be extremely lower than a one-shot local oscillator from the range of 800 to the 0. Okay, let's take an example. I have a superheterodyne receiver, and the superheterodyne has a frequency of an intermediate frequency of 500 kilohertz. Okay, so that's the intermediate frequency, sometimes called the fixed frequency. Okay, and what I would like to listen to is I'd like to listen to some channels between the range of 835 kilohertz and 935 kilohertz. Okay, remember that this is the frequency, not the angular frequency. So it doesn't really matter. It's just a scaling of 2 pi. If you multiply the entire equation by 2 pi, then you're going to get the same. Then you're going to get the equation above. Okay. So the question is how to find the range of the tunable oscillator. The minimum is calculated and the maximum is calculated using the same exact equation. F minimum minus Fi equals 835 minus 500, which is 335 kilohertz. And the same goes for the maximum. So the range is between 335 and 435 kilohertz. The question could show up in another way. What if I have a tunable local oscillator, okay, and its range is 200 and 300 kilohertz, okay, and I have already a fixed circuit that can demodulate the signal if it was centered at 365 kilohertz. The question is, what channels can I listen to? Okay, then I could calculate the maximum and the minimum using the same equations as well. FC minimum is 565 and the maximum is 665, and that becomes the range. Okay, thank you for your attention, and let me know if you have any questions. And remember that this document is posted, a link for that document is posted in the description below, and an Arabic version of this video is in the description below as well.